Guys, and welcome once more to this new video on my YouTube channel, where actually you are going to be solving a question on partial fraction mixed with integration actually. So this was a Cameroon DC examination for the mathematics paper 2 of June 2022 actually. So this was question 2 of that year. The question was asking us to express f of x in partial fractions where f of x equals 2x cubed plus x plus 2 divided by x squared plus 1 times x squared minus x plus 1. Hence, show that the integral of f of x from 0 to 1 dx equals ln of 2 plus pi divided by 36 times 9 plus 8 root 3 actually. Let's move actually into the solution of this question actually. The first one of the question is actually also express f of x in partial fraction where f of x equals to x cubed plus x plus 2 divided by x squared plus 1 times x squared minus x plus 1. So expressing this f of x in partial fraction is simply implies that this f of x actually is going to be equivalent to ax plus b divided by x squared plus 1 plus cx plus d divided by x squared minus x plus 1. Further simplifying, we are going to obtain 2x cubed plus x plus 2 to be equivalent to ax plus b times x squared minus x plus 1 plus cx plus d times x squared plus 1 actually. We obtain this by simply looking for the LCM, okay, on the right hand side, okay, and seeing the LCM on the right hand side, okay, is simply this same value. It implies once we are going to simplify the things, we are going to see that 2x cubed plus x plus 2 will be equivalent to ax plus b times x squared minus x plus 1 plus cx plus d times x squared plus 1 actually. Expanding the right hand side, we are going to obtain 2x cubed plus x plus 2 to be equivalent to ax times x squared gives us ax cubed, ax times negative x gives us negative ax squared, ax times 1 gives us actually ax, then b times x squared gives us bx squared, b times negative x gives us negative bx, b times 1 gives us 1, cx times x squared gives us cx cubed, cx times 1 gives us cx, d times x squared, okay, gives us dx squared, and then d times 1 gives us actually d actually. Bringing light terms together on the right hand side, we are going to obtain 2x cubed plus x plus 2 to be equivalent to a plus c, or other in bracket, times x cubed plus open bracket b plus d minus a close the bracket x squared plus a plus open bracket a minus b plus c close bracket x plus b plus open bracket b plus d close the bracket d actually. Here we can clearly therefore, okay, equate coefficients. That is, we can clearly see that on the left hand side we have 2, okay, that is the coefficient of x cubed actually on the left hand side is 2, and the coefficient of x cubed, okay, on the right hand side actually a plus c, from which we can therefore write as our first equation, that is a plus c to be actually the coefficient of x cubed on the left hand side, which is 2 actually. We do the same thing for x squared. Since on the left hand side we don't have x squared, we can therefore conclude that the coefficient of x squared, okay, on the left hand side is 0, from which we can therefore come up with our second equation to be b plus d minus a to be equals to 0. That's our equation 2. Equation 3 actually, we are going to see that taking the coefficient, okay, of x, okay, on the right hand side, equating that to the coefficient of x on the left hand side, we are going to obtain a minus b plus c to be equals to 1, which is the coefficient of x on the left hand side actually. And finally 2, okay, is actually equivalent to b plus d, which is going to be our equation 4 actually. So here we have a system of equations from which we have to determine the values of a, b, c and d. So that we can clearly see that from equation 1, if we substitute equation 1 into equation 3, we can actually come out with the value of b, because a plus c is actually 2. So substituting actually equation 1 into equation 3, we have actually 2 which is actually a, okay, plus c, 2 minus b to be equals to 1 actually, which implies that actually the value of b is equals to 1. Substituting the value of this b into equation 4, because if we substitute the value of b into equation 4, we are going to obtain actually the value of d. So substituting the value of b into equation 4, we are going to have actually b, which is 1, that is 1 plus d to be equal to 2, which implies actually that the value of d is going to be actually equals to 1, that is 2 minus 1 gives us 1 actually. since we already have the value of d, actually we can clearly see that we have the value of d. Okay, we can therefore substitute the value of b and d into equation 2. Since we have the value of b, we have the value of d, we can therefore substitute these two values, that is the value of b and the value of d, into equation 2. This is going to enable us to get the value of a actually. So substituting the value of b and d into equation 2, we have actually b, which is 1, d, which is 1, that is 1 plus 1 minus a to be equal to 0, from which we have the value of a to be equal to 2 actually. And here we have the value of a, we have the value of b, we have the value of d. We can therefore go and substitute those three values into actually which equation? We can actually substitute them into equation 3 actually. That is, substituting the value of a and b into equation 3, we actually get the value of c actually, because we have the value of a to be 2 and the value of b to be 1. So substituting those two values, we obtain the value of c actually. So substituting that, we are going to obtain 2, which is the value of a, minus b which is 1, plus c, which is equal to 1 actually, which implies actually that the value of c, okay, is going to be 0 actually, properly. Hence we can therefore conclude that the value of a equals to 2, the value of b equals 1, and the value of c equals 0, and the value of d equals 1, from which we can therefore come and substitute those values here actually in order for us to obtain our function f of x in partial fractions. That is, substituting the value of a with 2, the value of b with 1, the value of c with 0, and the value of d with 1, we actually get this expression actually. Further simplifying, we are going to obtain 2x cubed plus x, okay, plus 2 divided by x squared plus 1 times x squared minus x plus 1 to be equivalent to 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1. This is actually the expression of f of x in partial fraction as asked on the first part of the question actually. Yes. Okay, alright, in the next part of the question, we have been told that hence show that the integral from 0 to 1 of f of x dx equals ln 2 plus pi divided by 36 times 9 plus 8 square root of 3 actually. So to do this actually, we had actually this function expressed in partial fraction as 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1. So in order for us to prove this actually, the integral, to know that the integral from 0 to 1 of f of x dx is simply the integral from 0 to 1 of the element expressed, that of the element of f of x, of the expression of f of x in partial fraction. That is, the integral from 0 to 1 of f of x dx is equal to the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1 dx. That is, the integral of f of x is simply the integral of the expression of f of x in partial fraction simply. So you can clearly expand furthermore the right hand side, since you have the positives here, so we can actually expand this integral. That is, integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1 dx will be equal to the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 dx plus the integral from 0 to 1 of 1 divided by x squared minus x plus 1 dx. I have simply splitted this integral into 2, since I have a positive a plus here actually. So further simplifying this portion here, that we are going to have the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1 dx to be equal to the integral from 0 to 1 of 2x divided by x squared plus 1. So I can split this furthermore. I will have the integral from 0 to 1 of 2x divided by x squared plus 1 dx plus 1 divided by x squared plus 1 dx actually. Then plus this other part, that is plus the integral from 0 to 1 of 1 divided by x squared minus x plus 1 dx actually. So here actually you have to note that this actually and this are known integrals. That is, if we integrate this integral from 0 to 1 of 2x divided by x squared plus 1 with respect to x, we are going to clearly obtain a limit function here, because the numerator is actually the derivative of the denominator. So here there is no problem. Similarly, for it also is a known identity, that the integral of 1 divided by x squared plus 1 is simply tan inverse of x actually. Then our problem now is at this level actually. What then can we do here? I splitted this element. Why? Because you can clearly see that this x squared minus x plus 1 cannot be factorized actually. So reason why, since it cannot be factorized, that the discriminant of this x squared minus x plus 1, okay, is less than 0, that is this x squared minus x plus 1 can be factorized, then we have to think of obtaining actually a tan inverse function here actually. Yes, so that is the methodology which we have to use here in order for us to obtain this integral actually. So how first of all can we do that? We have to do that actually by reducing this x squared minus x plus 1 in this form here, that is x minus a half other square plus 3/4, okay, dx actually. The next thing which we are going to do is that we are going to make sure we have a 1 at this level by simply doing what? Factorizing 3/4 in the denominator. We are going to have this expression, that is this one remains on the, let us put back these ones, these two ones, let us put it back, and then at this level we have simply factored out 3/4 in the denominator, on which we are going to have 4/3 integral from 0 to 1 of 1 divided by 2x minus 1 divided by square root of 3 all squared plus 1. How I came out with this thing is quite direct, because if you factorize 3/4 in the denominator, here that 3/4 is going to be inside here, so adjusting the 3/4 inside here, we are going to have the square root of 3 divided by 2 actually, and the 2 is going to cancel with the 2 which we are going to obtain once we are going to do the LCM at this level here actually. So this actually is simply as a result of factorizing 3/4 in the denominator, we obtain this relation actually. Yes. Yes, so actually writing back what we have, that is the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1 dx equal the integral from 0 to 1 of 2x divided by x squared plus 1 dx plus the integral from 0 to 1 of 1 divided by x squared plus 1 dx plus 4 divided by 3, okay, times the integral from 0 to 1 of 1 divided by 2x minus 1 divided by the square root of 3 all squared plus 1 dx actually. The next step which we have to use, the next step which we need to do here actually is actually, at these things remain, these ones, let us first of all put it back again. So at this level, the next step which you have to do is actually to differentiate the interior here. Differentiate using the quotient rule. Actually, you're going to obtain that the differential of this element is actually 2, okay, times the square root of 3 divided by 3, and we simply put it in the numerator. So we put it in the numerator, we have to adjust it in such a way that it can cancel by simply putting that adjustment outside here, because you can see that this one and this one can cancel easily. So I'll explain back, that is I obtain the differential of this interior part actually, and from there I therefore putting it up, I have to adjust it by putting something outside. By simply putting this outside, it will simply adjust it, that is this, if this one and this one cancel, I will still obtain a 1 there actually. So this is the methodology which you have to use, that is differentiating this, putting it in the numerator and adjusting it by putting something, a constant, outside the integral actually, for it to actually cancel with what is in the numerator. That's the methodology here, and that is how we are going to obtain actually our tan inverse function from here easily, because the differential of this element is simply what is in the numerator, and clearly we can come out and we can conclude that this integral actually is simply equal to tan inverse of 2x minus 1 divided by square root of 3 actually. So that is the methodology which you have to use here, and that is what is there actually. So we are going to obtain the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1 dx to be equal to the integral from 0 to 1 of 2x divided by x squared plus 1 dx plus the integral from 0 to 1 of 1 divided by x squared plus 1 dx plus this one, this 3 and this 3 are going to cancel. 2 is going to go here 1 time, 2 is going to go here 2 times, so we are going to have 2 divided by the square root of 3 times the integral from 0 to 1 of the same thing which you have here, that is 2 times the square root of 2 divided by 3 or divided by 2x minus 1 divided by square root of 3 squared plus 1 dx actually. Yes, point you can therefore write that the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 divided by x squared minus x plus 1 dx is equal to, getting this integral, as I told you, we are going to have ln, okay, of absolute value x squared plus 1. This absolute value was not obliged for you to put it, because actually x squared plus 1 is already positive actually. Yes, but I just included it like for you to know that actually you can obtain something, you can be facing difficulties where you have the elements which are not actually positive. The reason why, let us just put this absolute value here, but x squared plus 1 is actually always positive. Okay, so you can remove the absolute value. In this case it works. Okay, putting the boundaries, that is from 0 to 1 plus this integral, that's integral from 0 to 1 of 1 divided by x squared plus 1 dx is actually tan inverse of x actually, putting the bound, that's it, from 0 to 1, and then plus 2 that is square root of 3 times, as I told you, this one is simply the tan inverse, this integral actually is actually the tan inverse of 2x minus 1 divided by square root of 3. Okay, I'm putting the boundary that is 0 to 1 actually. You see that from here we already obtained, we are already moving towards actually our proof. That is, if you simplify furthermore, we are going to obtain the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 divided by x squared minus x plus 1 dx to be equals to lower bound. That is, if we do ln of 1 squared plus 1 minus ln of 0 squared plus 1, we are going to obtain ln of 1 squared plus 1 gives us ln of 2, then minus ln of 0 squared plus 1 which gives us ln of 1, and ln of 1 is 0. The reason why I did not include ln of 0 here actually. Plus tan inverse of 1 minus tan inverse of 0, but tan inverse of 0 is actually 0, but tan inverse of 1 is actually what I have written here actually. Then plus 2 divided by square root of 3 times tan inverse of 1. If you put 1, that is tan inverse of the upper one minus tan inverse of this element with the upper bound included minus tan inverse of this with the lower bound included. That is, we are going to have tan inverse of 1. If you put 1, everywhere you see x put 1, you are going to obtain tan inverse of 2 times 1, which gives out actually 2. Then 2 minus 1, we obtain 1. 1 divided by square root of 3. That's why we have it here. Minus tan inverse of 0 times 2 gives us 0. Then 0 minus 1 gives us negative 1. Then divided by square root of 3, we then obtain minus tan inverse of negative 1 divided by square root of 3 actually. This is what we have when we actually input actually those boundaries actually. That is what we have actually. Yes. Okay, yes, writing back what we have, that is the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 divided by x squared minus x plus 1 dx to be equals to ln of 2 plus tan inverse of 1 plus 2 divided by square root of 3 times tan inverse of 1 divided by square root of 3 minus tan inverse of negative 1 divided by square root of 3 actually. So we know that tan inverse of 1 divided by square root of 3 is actually pi divided by 6, and tan inverse of negative 1 divided by square root of 3 is negative pi on 6 actually, for which we are going to obtain what, that is writing back ln of 2 and writing back tan inverse of 1, we are going to obtain the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 divided by x squared minus x plus 1 dx to be equals to ln of 2 plus tan inverse of 1 plus 2 divided by square root of 3 times 2 pi divided by 6, that is pi divided by 6 minus pi divided by 6 gives us 2 pi divided by 6 actually. We know actually tan inverse of 1 is actually pi divided by 4, and removing this square root on the denominator, that is multiplying both the numerator and the denominator by square root of 3 for this operation, we are going to have the square root of 3 times 4 times pi, that is 4 times square root of 3 times pi divided by, we are going to, in the denominator we are going to have 3 times 6, which gives us 18 actually. So looking for the LCM between pi on 6 and 4 pi divided by 6 plus 4 square, looking for the LCM at this level, that's the LCM between 4 and 18 actually, we get the LCM to be 36, and 36 divided by 4 gives us 9, then 9 times pi gives us 9 pi, 36 divided by 18 gives us 2, then 2 times 4 times square root of 3 times pi gives us 8 times square root of 3 times pi actually, for which you can therefore factor out pi in the numerator. We get therefore the integral from 0 to 1 of 2x plus 1 divided by x squared plus 1 plus 1 divided by x squared minus x plus 1, the x to be actually ln of 2 plus pi divided by 36 times 9 plus 8 square root of 3 actually, for which you can therefore conclude that hence the integral from 0 to 1 of f of x dx is equals to ln of 2 plus pi divided by 36 times 9 plus 8 times square root of 3. So thank you very much actually, okay, for watching this video. Okay, remain tuned therefore for a very next interesting video on further mathematics, and please don't forget to like, subscribe, share, okay, for YouTube channel to grow actually. So thank you very much, and see you for a next interesting video. Thank you.